morning session, and apologies to everybody that we're a bit over time, and thanks for putting up with the technical issues. So the third speaker, it's interesting. I didn't have to put in any effort to make an introduction for Josh, because every time I spoke to somebody that Josh is giving a talk, they would say, "Oh, I know Josh from X," and every single time it was a different thing. So, for instance, one of the people here, so he was in math camp, Math Olympiad training camp with Po-Ling Lo, when, and then also so Nikhil Srivastava is in the back of the room. So he wrote actually an extremely famous, the BSS paper on graph sparsifiers, this Ramanujan sparsifiers, when you were an undergrad. You worked with Nikhil and Dan Spielman. And then you decided TCS, too impure, going to do some pure maths. You did your pure math PhD at MIT. And then you decided, no. And then you did a bunch of bio work. And now he works at Anthropic. And I was at an Anthropic event a few weeks ago, and I was actually kind of blown away by the answers you were giving on the panel. He was talking about interpretability. I thought he was going to talk about interpretability today. I guess, are you? Okay, there'll be some interpretability. Maybe he's going to teach me some physics today. I'm not sure. But yeah, I'm very excited to hear your talk.
Great. Thank you. So I'm going to talk about generalization in the representations of frontier language models. I had another word in the listed title, which is computation, but I decided not to give a 90-minute talk. So we'll do this. And generalization is maybe the big question here, right? You train these models on some fixed large set of data, and then they do things that are useful to you on questions they haven't exactly been asked before. And that's proven to be quite valuable, increasingly valuable for society and in science. But it's somewhat mysterious, what they have learned from the data and what you can trust them for, right? How general is the solution, how reliable, and all of that. Maybe this is a bit of context everybody's familiar with, but here's a slide on model sizes, the x-axis, and flops for training is on the y-axis. They're certainly correlated. And if you were to play this, there's an interactive version. We play this as a movie starting in 1950. You have small models for short periods of time. And as you move up, to here, right, where, just in the last year or two, we're getting these language models, which are these data points up there, very high on the flop side. Enough so that there was an executive order from the Biden administration that if you train a model sufficiently high on this, you have to tell the government. Just in the last year or two. The models are also kind of increasingly capable. I was watching Dr. Coulson's talk yesterday about jokes and surprisal in jokes, which was really interesting, where you're looking at how human brains respond when there's some surprise or when there's some humor, and finding some correlations with the perplexity of GPT-3. But GPT-3 is not that good with jokes. And so I decided I would take the new Claude Sonnet model that was released a few weeks ago and just give it one of the jokes. So this was explain this joke. A thoughtful wife has pork chops ready when her husband comes home from fishing. And Sonnet says, I understand the implied humor. It's playing on the common trope of fishermen coming home empty-handed despite their efforts. The wife being, quote, thoughtful and having pork chops ready suggests she anticipated her husband would fail to catch any fish. What was impressive about this is I didn't get the joke when I was watching the talk. I assumed it was just 50 sexism, the wife is cooking dinner, whatever. And then it was oh, but he was supposed to bring dinner, and the model got it. I will say this was not true of the model Sonnet 3.0, which we'll get into more later. It didn't get the joke, but the absolute frontier of these models are actually starting to understand and tell jokes, and sometimes jokes that actually make you laugh. So maybe that's cool. That's progress. Okay, so maybe actually even before this slide, there's billions of these parameters, and somehow the capacity to recognize and understand and explain this joke is in them. These parameters are just in the form of weight matrices of neural networks. They're sitting in an Amazon data center when I talk to this model, right? And so, you know, these words get turned into numbers. They like multiply a bunch of other numbers, and like there's some mild nonlinearities, and out the other side comes this explanation.
Just like your brain.
Yeah, except it's a lot more wet in here, in my head. Though a lot of the data centers are water cooled, so it's also wet there too. And so it would be interesting sort of to know like what exactly is that pile of numbers doing such that it can do this. So just in general, like models can do impressive and useful things. They're also weird and like fail. So at the same time, if you ask this literal model, like how many R's are in the word strawberry, and you don't let it like count it out, you just say like, give me the answer. It says the answer is 2, which is embarrassing because there's 1 in the straw and 2 in the berry for a total of 3. And so like, why is it that like it can't do that, right? But it can do the joke thing. Okay. So if we're going to use these more, it'd be good to understand what's going on. I think generalization is kind of at the core of that, right? Like, what did it learn? Okay, so for this talk, I'm going to talk a little bit about model internals and the linear representation hypothesis, what that means. Talk about decoding things from superposition, which I'll define with sparse autoencoders. And then I'll just dive into some of the generalizing representations from a frontier language model, and then some future directions and like speculation. This is just like a very like grounding thing, just so we all know what we're talking about. I think everyone here does, but like, you know, if you ask Claude, you know, how can I assist you? It tokenizes into how can I, or 3 words. Each token corresponds to a vector. They're concatenated in some way and plugged into a neural network. You flow through. These are mapmels and these are nonlinearities. In the end, you have another list of numbers, 1 per word in the vocabulary. These are scores, and the highest scoring thing gets emitted as the next prediction, and then you crank that. Cool. So like you kind of, in the brain analogy, right, these are all activations are all happening. You can look at them. It's not that obvious what it means, in the same way you drop someone MRI and you look at the brain and you're like, that's a pretty color, but it's not clear what happened with the joke. But there is something you can do, which has turned out quite strikingly well, which is to make linear measurements. So you put a sentence through the model, and maybe I'll take advantage of having, you know, a whiteboard. So we have like the dog went, and the way that the transformers work is you just have a bunch of blocks, some of which operate in place, some of which move information around. Those are the attention blocks. And at any given model depth before the end, you could like look for this word in this position. What is the vector state there? You know, and so that's some vector state. We'll call this like x2, and this would be x1. Let's say we're doing it at the middle layer of the model. And you can make a linear measurement of that state by just dotting these all with any vector w. Okay, and so that's just like a linear measurement of the model state. And the observation is that for many choices of w, the score you get by these dot products is semantically meaningful and interesting. So this was a paper where they tried to find a vector w such that that dot product was something like the sentiment of the sentence so far, or the sentiment of the word from a sort of negative, which is red, to positive, which is blue scale. I like this because this paper is super simple. Like they just took examples of positive and negative things, and took their means, and then took the vector, which was their distance, and just are dotting with that. And what they found is, even though that sentiment vector was gotten from a narrow class of data, maybe like nouns here, it generalized quite well. So the same vector w dotted the internal state. Here we get like blue, it's positive, have complete confidence, brought joy, negative on misery and hate. But on, I guess, like the Amazon and Walt Disney in this particular model, I guess, didn't like Romney or Bashar Assad. And then in medical terminology, migraine is negative, remission is positive, and recovery is positive. And it also is cross-lingual. So this was on a model that was trained on text in multiple languages, and like the vector, you know, works in French. And so whatever we know about how these models are working, just the fact that there exists a vector, right, that when dotted, gives you some sentiment measurement, and that seems to be general across contexts is quite striking. And it doesn't tell you that the model is necessarily using this, but it certainly suggests that it's possible, right? Because what is inside the model, right? A neuron in a neural network, its input is just the weight times the state, which is a dot product. And so anything which is linearly accessible is the kind of thing that a neuron could specialize to. And if you put in a threshold, maybe it would just catch the positive part. And then it could do something else in subsequent layers. Yeah.
What is the nexus here that you're operating on? And there are like some...
Yeah, it's the residual stream vector.
Residual stream at a fairly high level for that. The residual stream at that position.
The residual stream at each token position in the middle layer of the model. Yeah.
So this is the same for all layers, or like are the differences how it changes?
Yeah. So if you tried to find a sentiment direction in a very early layer, it would not be that accurate, and it would probably just be identifying like the valence of the word. And so if you had "I'm not feeling great," then in an early layer on great, it would think that was good. In a middle layer, it'd be like not feeling great, and it would know that that was bad. And so the concepts that sort of emerge vary. Early in the models, they seem to be dealing with like tokenization. You split all the words into chunks, and then you have to put them back together, and then you process things, just where all the action is.
This does seem we're not quite seeing things like that in these examples, right?
Yeah, this one's not that strong. In particular, what we're not seeing is the flip that you get from the not. Yeah.
Well, the model was not trained on sentiment, right?
No, the model's just trained to predict the next token.
So what else can you pick out?
Yeah. We'll get to some awesome examples. That was just a nice example from literature. People have found stuff for sentiment and truthfulness for internal states of board games. So this is like if you saw a game in chess notation and you trained it to predict the next move in chess, to do a good job of that, you'd probably want to know the state of the board. But in chess notation, it doesn't get an updated state of the board. You have to figure it out by counting the moves. And it seems like you could linearly measure, is this square empty? Is there a pawn on e7, et cetera? And so the latent state there seems to correspond to sort of the state of the board. There's the Word2Vec stuff going back a while, space and time things. So I want to get to like some of the math of how this might be working, and then I'll get you to the cool stuff happening inside of Sonnet. So how can so many specific concepts be represented linearly, right? You might call this the blessing of dimensionality, maybe the phenomenon of superposition. So, in n-dimensional space, you can only have n vectors that are exactly orthogonal, but you can have exponentially many that are almost orthogonal. And so just maybe the super concrete math here is, suppose you had a collection of, capital N random directions in Rn. Any given data point was a sum of k of those. So it's a combination of k of these random directions together. You can sense which the k are linearly. So if you just take the dot product of some xi with one of those sums, that is going to be equal to 1 if they're unit, I guess, normed, plus something whose order is k over root n. And so if you have like 5 of these and the dimension is 1,000, 5 over the square root of 1,000 is small. And so you can tell the difference between a hit and a miss. And the latent dimensions of these models tend to be order of thousands, right? And so as long as k isn't too big, you can linearly recover exactly what was encoded in there. And the vocabulary here, could be quite large. You can have exponentially many that still have inner products of order about 1 over root n. And so you can cram a lot in, and you can linearly measure it if you have sparsity. So here's, I promised Bruno that I would shout him out. This is Olshausen and Field, emergence of simple cell receptive field properties by learning a sparse code for natural images. So what if natural images, which are also just vectors of pixels, right, were sparse combinations of some privileged directions? Maybe you could find that by optimizing some objectives of the form like you should fit your data as a sparse combination of things, and also it should be sparse. So a fit term and a sparsity term. And when you did that to the vectors of natural images, you got out things like this, okay, which are highly structured. And so you might hope that not only are interesting properties of the latent states of language models linearly accessible, but that that state itself could be represented as a sum of terms drawn from some large dictionary of sentiments and vocabulary and actions the model might take. So some huge dictionary of like atomic units, and any given state is like a sparse sum of those. This is just a prior, right? But you could try to fit a model based on that prior and just see which directions fall out, see which vectors it suggests you might want to measure about the state. And in that way, we might learn something about the generalization in these models. So to be quite concrete, right, we take the autoencoder, we interrupt it at some point, we decode into far more features than we have dimensions. Like we're going to use a sparse autoencoder, so it's a very simple way of decoding. So I guess I could have suppressed some indices here, but the basic idea is that we're going to represent X as a bias plus a sum of vectors drawn from some dictionary with some weights. Those weights we'll call the feature activations, and the directions we'll call the features. And the feature activations are just going to be a nonlinearity, a threshold ReLU, of a linear measurement of the state. And so it's kind of like a single layer hidden network. And then the loss is like an L2 loss, which is like, did I recover the state? And a L1 loss, which should reward sparsity. If these directions were like isotropic, right? Even isotropic, or they were just like Gaussian with some like SVD shape, but like drawn from that, then this model would give you a very poor fit, right? Such data would be badly approximated by a sparse sum of terms. And I think a lot of previous work on neural networks looked at the residual stream and modeled it as Gaussian blobs and looked at the weights and modeled them as like Gaussian transformations. And you're just thinking in the Gaussian world. But if you think in the sparse world and you train something here, something kind of interesting happens. So we train sparse autoencoders on the middle layer of Claude 3 Sonnet. That's a model that was frontier as of May. We unpacked its residual stream in the thousands into 34 million different features. And so here's one of them. And so so this is feature number 31,164,353. And it has an encoder vector that you can dot with the residual stream. So we just take a ton of data, pass it through the model, and just at every single token measure, right, with this dot product. And we're going to color the token by the magnitude of that measurement. It's white if it's 0. And here I am pulling forward out of maybe an order of billions of data set examples, the contexts where there's a token that had a high inner product with this.
So the inner product should be signed.
But we apply a ReLU to it.
Okay.
Yeah. And that's going to be what gives us the sparsity in the autoencoder story. Okay. So what we find is that for this particular vector that came out of the SAE training, there's a mention of the Presidio, a huge park right next to the Golden Gate Bridge. The suspension bridge and a similar coloring is often compared to the Golden Gate Bridge in San Francisco. Repainted every dozen years. Okay, so these are all mentions of like literally the landmark, the Golden Gate Bridge. Here are discussions of the Golden Gate Bridge in Korean and Japanese and Russian. And you can see that this feature is also activating there. And so somehow this vector is like, getting something multilingual. Yes?
Without bridge, because this was get activated?
A little bit.
Because if this is like the code-only model, like we see Golden Gate, this gate has large activation. It hasn't seen bridge yet, right?
Correct.
So that means Golden Gate will also be configured.
Yes, more weakly. And this is these models can take in. Oh yes.
The Japanese version, like it doesn't trigger the Golden Gate Bridge super well. I mean, it's light pink. I don't know how much you read Japanese, but like the English version, the Golden Gate Bridge trigger is much stronger. I'm assuming the brighter darker colors trigger more.
Yeah. So I'll show you on the next slide a histogram of how this plays out, so you can think about the relative quantitation. It is true it's somewhat weaker, but this is still enough to be meaningful. One last thing is that it also fires on images of the Golden Gate Bridge, so the model, can take in pixels and then, produce things. And so we also see activity here. Yes.
How did you know that this topic number 3 billion something was Golden Gate?
Good question. We looked at the data set examples where it was active. So coming out of this process, you just have a list of 34 million vectors. And then you can go through the a data set and select out examples where that feature is firing, where the dot product is large. So for every feature, you get a table of data set examples.
Like 50 billion labels.
Yeah. So there's two ways to do this. One is that we talk to the model, and we'll do this in a minute, actually, and just look which features are the most active on that prompt. And then we go and we inspect them. And so we were talking to it about local landmarks in the Golden Gate Bridge. And then we looked at what features were active. And then we came to this one and saw, indeed, it was not just general landmarks or something, but it seemed to be specific to the bridge.
So this is a noun, right?
Yeah.
It's an adjective. And you gave us an example of sentiment, which
Yeah.
is value.
Yeah.
Some of the features, are they abstract? Like,
Oh, yeah. We'll get to some cool ones.
okay.
But like, it's abstract as like generalized feelings of disquiet or like conflict in relationships. Yeah.
I'm still a bit confused. So for this example, like you showed this one of like several billion features.
Yeah.
Did you start this by saying, okay, I want to find the Golden Gate Bridge, feature?
No.
So how did you start this? You didn't start with this. I mean, did you just pick a random feature and then start? Like, this is,
All right.
you didn't analyze all 33 because in some sense, like if there are 3 billion features and one of them corresponds to some landmark, I mean, I don't know, that maybe is not doesn't sound
what?
doesn't sound special, right? I mean,
Yeah. All right. So let's just dive in because we're getting a lot of questions here. All right. So here's Claude. And on the right is this is a data set with 1 million features. And so on the right is like which of the 1 million features are active on this conversation. And I could say, tell me about UC Berkeley. And then on the right here, it'll take a second to render the feature portion. Here, this is the feature that is most active on this prompt. You can see which tokens have positive inner product, right, with the corresponding vector. If I want to understand what else in the entire data set has a positive product with that, I can go look at a list of examples. Yes. Yes.
Had a rel in its objective function, so it was ensuring that everything is non-negative.
Yes.
And here, all of them are non-negative, as you say, and then you were sorting by total activation sum, which is also well defined.
Yes. Yes.
That's a way to automatically discover everything.
but I discovered what?
Well, okay. So literally, so here we're just at the level of mathematics right now, right? This is like this is some vector in my list of 1 million, and then we've gone through a large data set. and looked for other places, right? And then we can look at this, and you can see it appears to be discussions of universities, right? Like these are just other places that is, both at the highest activations and also lower activation levels. Here we're talking about enrollments of universities, right? And so I'm not telling you exactly when this is active and not, but this is certainly related to, you know, many classes of university. We could attempt to summarize that as references to universities and colleges with factual details. I didn't summarize that. We had Claude summarize that because a million's a lot. And so we gave Claude these tables and we asked it to give a summary of like when things were active, and that's what these summaries are. And so one could then either search the summaries of these that have been generated by a model for things of interest, or you can just have a conversation and you can see what is showing up here and see if you can kind of learn some things from that.
So it's interesting, you know, you're pushing an interpretation that this is a feature that means something.
Yes.
But if you go back to your histogram,
yes,
it seems that the vast majority of information in the output of the neuron actually lies like in the big part to the left where like all the samples are happening. So is it that there's information that's just not being used, or is this actually not a Golden Gate bridge detector? It's just that that's what you see if you look for the outlines on the right-hand side.
It's a good question. So, there's a way to think about this and there's a way to test it. So just to rephrase the question, here's a histogram. And really, let me actually go back to the talk because I think that this histogram is a little bit even easier to see. This is like a little bit of a richer one. So this is for that Golden Gate feature. This is a histogram over a large data set of how active it is. That's the top part. You can see there's a very long tail on the right of large activities. There's a bunch of small activities down here. And then there's, of course, 0, which is 99.999% of the data is just not about the bridge at all. And also this feature is not firing, right? And the question was like, when I'm looking at this, should I think that what this feature does is the large activations? Or should I be like, man, most of the probability mass is here? Or should I do something in between, right? You could take an expected value where you multiply the probability by the magnitude. And if you do, which would be like, where's the quantitative impact of this feature coming from? If you do that, this crushes, and you maybe get a peak that's still a little bit over here, though it's a much longer tail. So, you know, there's sort of an a priori interpretation is like, well, maybe this is just that like our encoder is like a ReLU and linear map. And actually, if we had a stronger encoder, like a compressed sensing encoder, right, where you did some EM thing to like find an optimal representation, then you wouldn't have those small activations. With a linear ReLU, you have a shrinkage problem, right? Famously, where, you know, if I want to move the threshold, I'm going to shrink everybody down here. And so there's some trade-off between the large. So that's quantitative questions. The other thing you can do is you can do a forward pass of the model, look which features are active, find and then ablate them, and see how it changes the model's output, right? And so you can see, like, you know, do ablating the large numbers have significant impacts on what the model says next, right? Or the small ones, and are these big levers of control, basically? And we find that is true, right? And so it's possible that, for example, that the rest of the model has some like noise suppression stuff that can tolerate these, but certainly the significant activations are causally relevant for a lot of tasks. I will say that, you know, this is an example of what we would call a relatively monosemantic feature, meaning that the difference between data set examples of large activations and small ones seems to be one of like kind or degree rather than meaning something quite different. So the largest activations are like that is the bridge. The smaller ones, like actually, like, and these are down here, right, have the bridge in other scenes, or are discussions of like other parts of San Francisco, or it's words in discussions of the Golden Gate Bridge that are more distant from the bridge, but the model was just thinking about the bridge, but now it's doing something else. And so this feels very monosemantic. There are some which are more polysemantic, right? There's no guarantee that this would happen. And often we do see features where what's going on down here and up here seem like quite different. And that would be a problem for interpretation. If you want to interpret the model in terms of this feature, recognizes this and does that. But like actually up here and down here are totally different stories. That's not a very good interpretation of the model. And so, something we're careful about measuring is the degree of monosemanticity. Here, I'll say we had Opus, another model, grade these according to a text description. So we describe, we think this is about the Golden Gate Bridge, and then we gave Opus a random selection of data set examples from here and asked it to grade if they match that description. Dark red is very much, this is related, this is vaguely related, and blue is, this is totally irrelevant and not matching.
But I don't think you have quite answered the whole question.
Okay.
One, does it causally affect the recognition of the Golden Gate Bridge?
Mm-hmm.
The other one, does nixing it not affect cumulatively a ton of other things? Like neuroscience did it, where they were like, hey, look, we find cells that are tuned to color, therefore this must be the area for color. And what we find is that basically the areas do like all kinds of things, and they're apparently really relevant for.
Yeah. So go ahead.
I mean, pulling up the thing is, if you do the simulation study and you mix this, there probably is, I'm just not sure what that would convince me of, right? Because if it operates together with a bunch of other things, like if my baseline hypothesis, I guess, is that things are complex. And everything is complex and depends on many things, because this is how it's used. This is presumably from some middle layer. This is how they're used later on. I'm not entirely sure what I'm supposed to get from this. Like it seems like you're parsing an interpretation. You started out by saying, I want to find an interpretation here, and there's so many things. There's so many things to correlate to. You found some correlation, but why should I be convinced that this is related to what the model is actually doing?
Can I batch up any other questions on this forward? Yeah.
So maybe related, but if I was just looking at the example you had, and white was 0 weight, right? No weight. And I was looking at the different languages. So this could be happenstance, it's just a single example. But for example, if I look at the Russian, the word bridge is not picked up at all. It's 0 weight. So if it is semantics, then you should be, so, most of the Russian for bridge, it's just not being picked up at all. So if it is semantics, you shouldn't expect that result. But again, it could be happenstance, just a single example. But have you gone across languages and seen what is happening with the same mechanism?
And any more? Yeah.
My question is pretty independent of all of these questions.
All right, then we'll do that later. Anything else on this theme?
Do you have quantitative study of how many of the directions are monosemantic and how many of them are multi-semantic?
Yes. Okay. So let's back up a little bit. The first thing you might do with one of these models is try to interpret the neurons in the models, right? Like, here is a neuron, it's a computational unit, read, nonlinearity, right? That's what it does. And I think this is certainly what neuroscience did, right? Like, what is the role of this neuron? And I think that both what is mostly found in neuroscience and what we also find in these models is that they are polysemantic. There's distributed codes. They are used in many systems cooperatively. If you do this exercise and you look at when it fires, you'll find that the most extreme activations have some pattern. But as you move your way down, they're involved in like a host of different activities. And so, you could, one, it's hard to interpret the neuron from the activation alone. It's hard to predict from, if I gave you a text together with my description of the neuron, and you told me when it should be active, that would not be a good match to when the neuron is actually firing, right? one thing you might think, well, if it's a distributed code, then perhaps it is combinations, linear combinations perhaps, of neurons that represent something coherent. These all fire together, and when that pattern happens, that's when you see this particular event. I think of what this SAE might be doing, I mean, literally in some sense, it is defining a linear combination of neurons, right? Such that there's a much smaller set of those that you need than the set of active neurons to describe an example. And then we can quantitatively measure the degree to which that linear combination of neurons is more interpretable in terms of when it is active, in terms of a brief interpretation, right, than the neuron basis that you would naively be working in. And you can also check for what happens if you do ablation and activation experiments, both in specific domains of interest to see what behaviors are damaged, and also in sort of free play to see what behaviors get induced. And to the extent to which these hang together, more coherently, right, than in the neuron basis, you've made some improvement. And then the other question is like, do they help you, predict behaviors, right? Do they help you design interventions, right? Do they help you learn anything about the model, right? Because ultimately you want to cash this out not in a perfect interpretation. It seems quite unlikely that with something this fuzzy, you are going to get a perfect interpretation, but in something that's like better than your baseline. And so I want to, so here's one thing you can do. One thing you can do is you can stimulate this during generation. And so here's a case where if you ask the base model, what is your physical form? It will say, I don't have one. I'm an artificial intelligence. But if you stimulate this direction by adding this vector to the residual stream, it will say, I'm the Golden Gate Bridge, a famous suspension bridge that spans the San Francisco Bay. Which makes me think that this isn't just correlative, but causally related, because if you add it in, the model says it's the bridge. So here is another feature that we noticed fired on some errors in code. So this is a typo where right is spelled incorrectly. And this is a data set example, right, where this feature is active. And the same feature is active if you try to divide by 0. Or if you gave -1 as an argument to something that assumed it was going to be positive. And if you run a forward generation on correct code where you add that feature in, the model predicts a traceback completion, which is what would happen had there been an error in the code. And if you have an error in the code and you subtract off this direction when you're doing a forward pass, it gives the answer as if the error had been corrected in the code. Yes?
Where you it's like multiple layers.
Yeah, so for this, what we do is we work only in the middle layer and we are clamping it. So we are basically fixing the projection onto that direction.
And then going through.
And then do the rest of the, so you do a forward pass up to here, you take whatever the value is, you take its projection on this direction and then you extend it, and then you continue an ordinary forward pass.
I'm just wondering, can we assume the model get the language syntax right? Like previously for the Japanese, you show the Golden Gate Bridge, but the Japanese had a negation at the end of the sentence. So is this model just capturing whether Golden Gate Bridge is mentioned? It can be totally say it's not a Golden Gate Bridge.
Yeah, I think that this feature would be about, is that concept being discussed, and also depends on which token. So, I think one thing I'll say is like, and one problem with this, right, is that like, it's clear from looking at data, right, that these are quite localized, right? It is not every token, it's only some, right, around, it seems like where the error might be. But when we are doing the steering, we are constitutively setting this on every single token, which is probably extremely ungrammatical from the perspective of a model. This reminds me of, actually, I don't know if any of you know like Jeremy Freeman in the neuroscience world. Yeah, so one of I was at Wired magazine, was one of the weird things I did some years ago, and I did a story on some work of his and Misha's on zebrafish. The zebrafish swimming over some striped patterns, and they were recording every neuron, right, with calcium imaging, and then they did like some PCA on that to identify neural tunings. And they'd be like, here are the neurons associated to like turning left. That set includes, of course, perceptual neurons that were recognizing the grading pattern, any degree of like cognitive navigation, decision-making things, and then the motor neurons that made it turn in response to that pattern. And all three of those would show up as being correlated with that stimulus. But of course, they do very different things functionally. And so just because we see a feature which is lighting up, on errors in code, is that like recognizing it, right? Is that like deciding to do something based on that? Is that like triggering the traceback thing at the end? And all three of those could show up with the same data set correlations. And so I think that this method, when we go and look at these features, even when it seems like the data set examples tell a coherent story, that doesn't tell you what this is doing sort of in the model's processing. And to get at that, we need to not just do stimulation in the inside and see what happens at the end, but start to look at how these actually connect to each other with, I think, much more serious experiments. Yeah.
So what if you're clamping or you're stimulating the whole vector?
Yes.
What if you vary the size of the vector? You threshold it. What's the minimum amount that you need in order to get these effects? Just to get a rough sense for what fraction of the total number of units in that layer are important for that behavior.
Yeah. So the question is like, what happens if you vary the magnitude of the perturbation? Right. And so here's one. So this is a feature about cherry blossoms, discussions of cherry blossoms. Now, it's maybe more specific than that, I don't know, but we can steer with it. And so I'm going to, let's do 6. And so here we can have, we can talk to the model with this feature turned on to varying degrees. So each column is a different amount of the vector being added back in. And we can ask a question like, what should I wear to a wedding? Okay. So this is like, the type is pretty small here, so I'm going to zoom in and we can scroll over. So on the left, when you don't stimulate this direction at all, it just gives like some standard advice. When it's at 30, it gives standard advice, but with a bit of a twinge. It's like saying your skirt might be pink or yellow or blue, but otherwise it's like pretty basic. Now it's like definitely pale pink. But still, this seems to be sort of similar in what it's saying. Now it's just like cherry blossom trees are a classic choice for weddings. It's a great backdrop. You could wear a colorful azalea shrub. For a more elegant look, try a Japanese maple tree. And now it's just not even answering the question about the wedding, because you're sort of screaming cherry blossom trees, right, in the middle of the model. And so it's just cherry blossom trees are beautiful when they bloom in the spring. And it's just talking about it. And when you're up here, it's just like, cherry blossoms are great in DC. Here's some photos, right? And so it does seem like there's a difference in qualitative responses in response to the quantitative changes, yeah.
It's related to this, because you can climb on the code error. Can you climb on things like fake news? And then you just create a worldview that hopefully has only correctness.
Yeah. So this is part of the question is like, can you just like remove bad stuff by clamping these things negatively? So there's actually, our societal impacts team looked at this from the perspective of bias. There's a nice paper recently where they took 30 features that seem to be associated with bias on the basis of race and sex and age and ability and all these kinds of things, based again by looking at the data set examples of when they were active. One really interesting one is there will often be features which are one for like the thing and one for discussions of the thing. So there was a feature for like discussions of pay inequity across gender in the workplace, which is not the same thing as like somebody enacting, that thing. Fine. And so they tried steering with these things, and they found that most of them didn't do anything, or if they did anything when you steered with them, it was to damage the model. Right? Because once you go high enough here, it's very bad. But there was a narrow window where it seemed to not damage the model, and 1 out of the 30 successfully like reduced bias on some axes. Some of them actually went the wrong way. You thought that increasing this was going to reduce bias, but it actually like increased bias. Because again, it was hard to tell like what that vector is meaning, right, just from the data set. And so that's a 1 in 30 hit rate. And it also just feels very crude. Because another thing you could do is you could just, if you have the model and all of its weights, you can just in the system prompt say like, it recognizes fake news, just say like, I don't know, like don't give fake news. There's an example that, yeah.
Or that over time, maybe, yeah. And I see there are like many glorious.
Okay.
So maybe if you did want to have some.
Yeah. All right. Let me just wrap momentarily. So these were a bunch of features. I think that I wanted to give it, because we have a really smart audience here, I wanted to say that one of the big open questions is how to bake in things that are beyond sparsity. So sparsity is the only prior that we put into this, and we found stuff that was interesting. But like we might want something about compositionality, that these features should like be like, statistically uncorrelated or have different effects. You might want some hierarchy. The world has like hierarchy and connections, and these are all just one hot. There's geometry in the residual stream, like adding 1, it turns out, is like a rotation that like moves all numbers together. And like the computation isn't being got at here, just the representations. So if you're curious about those things, this is my favorite paper on this from Martin Wattenberg and Fernando Viegas at Harvard, where they just describe a bunch of the things you could imagine working here. And then I think a question is like, can you go beyond the SAE and just try to fit something that has these in it? And you should just see better recovery or sparser recovery. There should be a quantitative signal. And then you could also look at them for a qualitative one. That's my open questions. You can try these yourself. There's like SAEs that Google open sourced. So, the Claude ones, are behind closed doors because it's a big proprietary model, but like you can get started, right? There's like actual examples out there. And then last, this is a paper from a few weeks ago. You can do the same thing on any kind of data. Here is ESM, which is a protein language model, and they did the same SAE scheme we did on latent representations, and they try looking at like when are these active, right? And if we turn them on, how does it change the proteins that get generated? And they found a lot of pretty interesting, apparently interpretable, biochemical things showing up in the representations at a rate that was like 10 times larger than if you'd looked at the neurons of the system. And so I think that, in general, like these models can do interesting things. If we can get inside them, we might learn about the world, right? Whatever they know about the world, we can learn, and then we might be able to make them better and control them better. And that is probably my time. There's a lot of people at Anthropic who work on things. Here are some of them who've worked on this work from the interpretability team. And that is my time. I'm really happy to talk more about this during the break and lunch.
Yeah, so would you say that this is actually a good approach for alignment? Like you were talking about the bias thing, but are there any like more features that you could like really push and that makes the models like align?
So I suspect that steering is like a last resort for controlling models in the same way that surgery is a last resort for like healing somebody. I think that like, I think of this stuff as being like an imaging technology, and the correct response is like put a cast on or do physical therapy or something. So like, I think that this is a really good diagnostic tool for understanding where things are coming from, but that I think that probably things like fine tuning and prompting are better ways of adjusting behavior.
So there are in principle differences in detection when you look for some sort of feature theory in steering when you use that to change the behavior of the model. It's sort of surprising that they take the same form. A priori, right, what may work for detection may not work for steering the model. Any thoughts about why this is happening? Like what property of the model enables that?
I mean, I think that like if this kind of, I mean, it's certainly wrong, but if this like there are atomic units hypothesis is true, then you might ask, is that unit present? And what happens when that unit is present? And they refer to the same unit. And so in that case, the vectors aren't the same that you use for the encoder and decoder, but they are referring to like one object. Yeah.
I'm curious, in your sparse autoencoder, when you estimate the coefficients, it looks like we're just doing inner products and we do. Normally we solve like an optimization problem, L2 plus L1. You try to, because you have this explaining away interaction between the coefficients. So I'm just curious, have you tried that? And does it make any difference? Do you get more accurate or meaningful?
Yeah, so for the training process, you don't want to put that in the loop because it's pretty expensive and you can't do gradient descent. However, once you're done, you could kind of remove the shrinkage in that way. And we find that that helps. There's also a trick called jump ReLUs where basically you put a discontinuity in and that ends up being essentially as good as doing the ex post, EM trick.
When you just do these things, the model just still is grammatically correct no matter what. Was that not a surprise at all? Because maybe
the model completely barfs when you like put it high enough.
I see.
Yeah.
My other question is for any noun, like we just had Golden Gate Bridge, there's a feature associated with it, but if I picked a different landmark, do you think you'd be able to find some sort of direction that really lights up for that landmark?
Yeah, so the number of features that we use is a choice we make. We can break it into 1 million pieces or 34 million or 100 million if you spend enough money. And you can look, when does this particular object get its own feature as a function of that resolution? So the bridge did not have one at 1 million and did at 34 million. There are other rare landmarks that like the model knows about, but at this resolution, they get grouped with other things.
I think I will apologetically stop questions there. I see the personal frowns I'm getting. Sorry to both of you. Just in the interest of time in the lunch and the panelists need to go to lunch together. I will say that, what are the days we here this week?
I'm here all the rest of today, and I'll be here tomorrow as well.
So
I'm happy to.
Find a nice way to have like all of us around and we can ask more questions.
You can hot seat me. Yeah.
Is there a reception today?
There's a reception today at 4.
Okay.
And I'm happy to take questions for all of that. Yeah.
Speaker question. So I apologize to everybody, but let's thank each other.